Over the past decade, the National Science Foundation has spent billions of dollars trying to improve our understanding of science, technology, engineering, and mathematics. Every year, nearly $1 billion of that money is spent on education and training. Since 2000, every 3 years, U.S. 15-year-olds are tested on an international exam to gauge their understanding of math, language arts, and science. Despite great efforts to the contrary, we can see that results in math and in science haven't changed much. In fact, the National Center for Education Statistics recently came to this same conclusion. STEM stands for science, technology, engineering, and mathematics. Unfortunately, when people say STEM, they often mean SM. Engineering and technology remain largely untaught in U.S. education. When they are taught, it is most often as an elective, rather than part of a student's core education. This is because engineering and technology are not part of the core curriculum. Even the schools that do teach engineering and technology have to make sure that whatever they do aligns with established core standards. Unfortunately, students continue to struggle to understand basic mathematical concepts, such as variables, functions, and how to apply math to the real world. At the same time as technology and engineering are being excluded, we hear reports that by 2020, the U.S. alone will need 1.4 million computing jobs filled. At the current rate, there will only be 400,000 students who have had any computer science in school. These discrepancies are not going unnoticed. Local business leaders ask that we prepare students to handle computing in their jobs by 2020. A common solution that is being proposed is to provide every student with electronic devices. Many argue that if we give all students either a laptop or a tablet, that they'll come to figure out the technology on their own. These approaches, while noteworthy, fail to fully address the problem. Providing tools without understanding has never been a successful approach. Consider that we're this dot here, and the technology we want to master is here. The logic is that if we move forward toward that goal, we'll eventually attain it. Unfortunately, many proposals don't go far enough. You see, technology is also moving forward. If we want students to be technologically savvy and ready to master the world when they graduate from school, we need to project where the technology will be when they graduate, and move instead to intersect it. There's a solution that may address both the concerns over science and mathematics and technology and engineering. Computational thinking. Computational thinking is a way of using logic to solve problems through the use of computers and technology. It involves the process of formulating and organizing problems by finding patterns, of creating abstractions and algorithms. We then use technology to automate those abstractions and to collect and analyze data. Computational thinking teaches us to be able to use these analyses to improve our world through technology. We then generalize these solutions to solve other problems. Learning to think computationally may actually strengthen students' understanding of math and science. Research shows a strong correlation between mathematics performance and computer programming. Even better, learning to program has also been shown to lead to increased interest and effort in applying mathematics. So how do we foster computational thinking? The United Kingdom seems to have realized that in order to better prepare their students to be masters of the technological world they will inherit, they must start early and continue with learning technology throughout their formative years. By the end of 8th grade, all pupils are expected to be able to understand and apply the fundamental principles and concepts of computer science, such as abstraction, logic, algorithms, and data representation. Students ought to be able to analyze problems in computational terms. They ought to have repeated practical experience of writing computer programs to solve these problems. Students ought to be able to evaluate and apply information technology, including unfamiliar technologies, in analytical ways to solve their problems. Through doing this, students will become responsible, competent, and confident users of information and communication technologies. There are myriad ways we can promote computational thinking. Young children are wildly curious about the physical world and how things work. Early on, we can teach them about simple machines and have them build their own to solve simple but common problems. There are an increasing number of apps for tablets that kids can use to learn engineering and coding principles. A recent study that examined 45 programmers' experience in learning to program found that nearly 75% of those surveyed began coding to either make or cheat games. Learning to make games is a great way to learn to think computationally. Let's consider a simple side-scroller game like Super Mario Bros. Playing the game doesn't require any mathematical thinking, but in programming the game, students can use several mathematical concepts, such as variables, functions, arrays, the Pythagorean theorem, and many more. There are a number of simple programming tools that allow students to learn to code games by dragging and dropping commands. This is called visual programming and is a great way to learn to think computationally and get a first experience in programming. There are a number of visual programming tools available for kids to learn to make their own games, such as Scratch, GameSolid, GameMaker, Sploder, GameStar Mechanic, Alice, and Tinker. Then, students can move on to learn textual programming languages, such as JavaScript, Python, ActionScript, PHP, Lua, and so on. And teachers don't have to start from scratch to do this. There are organizations who have now assembled curricula that teachers can pick up and use to teach children programming, such as Code.org, CodeHS, Code in the Schools, LearnStreet, Code Adventures, Code Combat, Khan Academy, Coursera, and edX. We envision students then using their coding skills to manipulate and create physical devices, such as the LEGO Mindstorms robots, Arduino, a small microprocessor that can be used as a way of collecting data for science and math classes, or the Raspberry Pi, a programmable mini-computer, or working with advanced robotics and projects. Learning to think computationally doesn't mean every student will become a computer scientist or engineer. Consider why every student learns about biology, history, chemistry, language arts, and physical sciences. One view is that learning about these subjects better helps us to understand the world we live in. As we better understand the world, we gain better control and mastery of it. Well, technology is part of the world we live in today, and there's every indication that the world is becoming increasingly technological. If we want to have power over the technological part of the world that we live in, students need to learn to understand it from an early age on. People will still become sociologists, medical examiners, weather forecasters, artists, construction workers, writers, linguists, programmers, and so on. Only now we'll have more people in other fields who understand the technology better such that they can make it work for them and adapt to their needs. By fostering students' ability to think computationally from an early age, we help them become masters of a technological world instead of slaves to it.